The original motivation we had for studying the weak field limit of the Einstein equations was that it was a first step towards studying or recovering the Newtonian limit. Now we are going to do just that, to take the second step and study the Newtonian limit in the case of a point particle. Okay, so this action, as we have written many times, is given by this integral and we know that the weak field limit can be studied by studying this expansion considering h and chi very small. So as a first step we just replace d mu nu by this expansion or by this expression, okay, and okay, we have minus mc psi eta mu x dot nu plus chi h mu nu x dot mu and the square root extends up to here. Okay, in order to expand this square root, we extract this first term as a common factor, and then okay, let me put this in this form, and okay, if this is small with respect to 1, okay, this we can expand this square root in this form. This is 1 plus a half chi h x dot divided by eta x dot plus terms of higher order, and now we multiply by this square root, we have the square root of eta x dot plus a half of chi h mu x dot nu divided by the same square root of eta x dot plus terms of higher order. Okay, the next step will be to work or to rewrite this action in the static gauge. The static gauge is the one in which the evolution parameter is just x0, okay, and so it can be identified with ct. And doing this, we have minus mc squared from this dt. Okay, and remember that this in this gauge x dot 0 is 1, but x dot I is 1 over c differential of dxi dt, so this is vi divided by c. So what we have here is v squared divided, with minus, because of the signature of the metric. So this is the first term, okay, plus a half chi divided by 1 minus v squared divided by c squared. And now we have to decompose this h mu nu x dot nu into 0 and I components. Okay, the 0 components are multiplied by 1, so we have h0 0. The mixed components h0i and hi0, they are added, so to get a factor of 2, and you have a 1 for the component 0 and vi divided by c for the component I. And next you have the completely special component, so this is vi divided by c and vj divided by c plus terms of higher order, saying chi. Okay, for the moment this is what we have, and I am going to ignore, now I'm going to expand this square root of g, ignoring all the terms of which are of order v squared divided by c squared squared. Okay, so I am going to just take the first relativistic correction if you want. Okay, sometimes I write m equal, sometimes I write this, but because in some places I do an approximation and in some places I just take the exact result. Okay, I think I don't need this. So first we have this term, okay, plus terms of second order in V, plus a half chi 1 plus v squared divided by c squared plus terms of higher order in V, and then all these terms with h00 plus 2h0i vi divided by c plus hij vi vj. So vi vj divided by c squared plus terms of higher order in chi and so on. Okay, let me multiply everything inside by mc squared. So we have this term, which is well, you can consider it in many ways, but it is certainly a total derivative, so let's ignore it, plus a half m v squared. This is the kinetic term of the particle in the Newtonian limit, and this is the thing that you expect in the Lagrangian, plus a half chi, sorry, minus, and then here mc squared plus m plus a half mv squared, and all these terms that correspond to the gravitational field. Okay, I am going to remove many of them. I'm going to make another approximation, but I wanted to keep this because what this expression reflects is that all the energy couples to the gravitational field. It's not just the mass, okay, here it is multiplied by c squared, but if you rearrange things, clearly what matters is m, but also the kinetic energy contributes to the total gravitational charge, the thing that acts as active gravitational mass, if you want. Okay, now I am going to make a further approximation. I am going to ignore all the terms which are of order h times v squared divided by c squared, because I am going to consider them much smaller than 1, and then in this approximation we get a half of mv squared minus a half chi c squared m h00 minus chi m c squared h0i vi divided by c. Okay, to this order, and we have to remember the definition of this Newtonian potential phi, okay, or at least the thing that plays the role of Newtonian potential in this limit. So essentially we wrote that chi c squared divided by 2 times h00 was phi, the gravitational potential. And we are going to add to this this definition that H0i, well, chi c squared H0i, I'm going to call AI. It's like a three-dimensional vector, which is the kind of vector that one considers in Newtonian theory. Then the action becomes in this limit the kinetic term, the expected kinetic term, minus m times phi. Okay, if this is the gravitational potential, at least, well, in the Newtonian limit is what you would really call the gravitostatic potential, because just like the electrostatic potential. And multiplied by m is really the potential energy. So this is the other part of the Lagrangian of particle coupled to the gravitational field in the Newtonian theory. But there is another term, which is this one. Okay, and what is this? And also multiply by m. You see that it is similar to the coupling of an electrically charged particle to the spatial components of the electromagnetic field. They couple through the velocity. This is to be expected because, after all, we have discussed this is the only kind of couplings that can be admitted because they have the right properties and so on. So why did I write this 2 here? I don't know. Okay, in other words, we have recovered what we thought was the Newtonian limit, but there is an additional term that we didn't expect. This additional term is probably weak. It has not been, it was not observed because it is too weak. It gives rise to very weak effects. So the Newtonian theory did not even consider it. But somehow it is to be expected. If you have in a relativistic theory, in a special relativistic theory, it is not enough. You cannot survive with just gravitostatic potential like this phi. Just like you cannot survive with electrostatic potential only. You need something else, because otherwise you would violate the principle of special relativity, and you would not have waves and other effects, and you would have instantaneous propagation. So something like this is expected, and indeed this gives rise to what are called gravitomagnetic effects. If you now replace this phi by the potential created by another mass, say I can write it a small m if you want to distinguish it from this m, you just recover exactly what you had in the Newtonian limit. Okay, so summarizing, in the limit in which the speeds are small and the gravitational field is small, the gravitational interaction that we have introduced, this one, it has exactly the properties that you expect in the Newtonian case. We have recovered two things, not just the form of the Lagrangian in general, but we know that this phi has also the form that the Newtonian potential has. There is a new term, which is not, this is not a contradiction, it's just that all the effects that are produced by this term are so weak. Okay, it already has this vi over c, which is small, not as small as v squared over c, but still small. This is an important suppression in the Newtonian limit. So the effects will be very small, and you don't need to, well, they are not really included in the Newtonian theory, and for a good reason. Okay, they work. It works quite well without it. But the moment you want to make more precise measurements, something like this should be added. But then, just like in electromagnetism, you would have to add field laws for this AI, add more equations to the gravitational field. You have 4 equations, 4 Maxwell equations, so you need something else also for the an improved theory of gravity. Okay, as we have discussed, this improved theory of gravity needs much more than this just AI. This AI, it also needs this Hij, which we have ignored because it is very, very strongly suppressed by these factors. And even if we add that, we will get a special relativistic theory which is not fully consistent. You need to add corrections and so on, in a way in which in the end you end up with general relativity.